Hello, Chem 111. This video is about transition metal complexes and using the spectrochemical series to understand color in those complexes. So the spectrochemical series, or one version of it, is written here at the top of this slide. And what we have is just a series of ligands that we commonly see in transition metal complexes. And the less than sign is just showing us that here at this end, we have what we call weak field ligands. And then at the other end, we have strong field ligands. And what that means is weak field ligands cause a small octahedral splitting, delta O. Strong field ligands cause a large octahedral splitting, delta O. And those large and small splittings are energy splittings. So I'm going to illustrate this with an example that we talked about, at least in my section. And the example is copper complexes. So we saw, I put a picture on my problem set, that copper with 6 waters around it in an octahedral complex is blue. And we saw that if you replace those waters with chloride ligands, that complex is green. Now, to understand this, we need to think about what the color means for the color that is absorbed. And so if something is blue, you use the color wheel and look at the color opposite. This means that the complex with water absorbs orange light, and the complex with the chloride ligands, which is green, absorbs the color which is opposite green on the color wheel, and that is red. Okay. Now we need to look at the d orbital splittings to see what's happening when this light is absorbed. So in an octahedral complex, copper 2+, like any other ion in that complex, has its orbitals split, and you will have gone over in class why this is, into 2 sets of orbitals. Okay, and you might have used labels on these orbitals. These are symmetry labels, T2G and EG. You might not have used those, it's fine. So copper, let's just make sure we know. So we're dealing, you can prove to yourself, hopefully now, that copper in both these complexes is the copper 2+ ion. Neutral copper has the electron configuration argon 4s1 3d10. Remember, it's one of the 2 exceptions in the first row. And copper 2+, therefore, is just argon 3d9. So copper 2+ over here, before it's in an octahedral field, looks like this. And then when it's split, the 9 electrons look like this. Okay, so when light is being absorbed by this complex, you're taking some electron from down here in the lower set of orbitals and putting it up here. And this splitting here is your octahedral splitting, delta O. So if we go back up and look at what we wrote for the hexaaquo and the hexachloro compounds, we can see that there are different octahedral splittings. One corresponds to orange light being absorbed by that electron, and one corresponds to red light. So we could draw those schematically. And the key point here, actually I'll use colors again, which is that the energy of red light is less than the energy of orange light. And this is something that you need to either know or look up. So the visible spectrum, red is the low energy, high wavelength end of the spectrum. And so it is in fact lower energy by a little bit than orange light. So if we draw 2 different splittings, so I'm just going to draw the d orbitals in the octahedral complex here. So just very schematically, here would be one splitting, and then here would be another one. Both of these complexes, because they're both copper 2+, still have 9 d electrons. but the delta O's are different. And so I've drawn a smaller delta O here for the red light, and here would be a larger delta O for the orange light. And so now, since we analyzed which complex is absorbing which light, we can write underneath these that this, with the larger splitting, is the complex with the water ligands, and this, with the smaller splitting, is the complex with the chloride ligands. So how this relates to the spectrochemical series is that if I look at the chloride ligand and the water ligand, and I go back up to my spectrochemical series, in fact, I see that the chloride ligand is a weaker field ligand than water. So it is consistent with the spectrochemical series that water causes the larger orange octahedral splitting. And just one note here, so in this case, water causes a splitting that is orange light, and chloride causes a splitting that is red light. That is not consistent across different complexes, as we'll see. But what we do know is that in any complex with the same metal, water will cause a larger splitting than chloride. So those colors won't always be red and orange. All right. So that's example one. I'm going to give you another example now and allow you to analyze it using the spectrochemical series. Okay, so example two is I have two complexes, and they are, again, an octahedral water complex, this time with nickel. And in this case, we're going to have an octahedral complex with the ammonia ligand. All right, so we have those two complexes, and one of them is violet or purple, and one is green. Which one is which? All right, so you'll have to use the spectrochemical series for this, and you're welcome to stop the video now and to try to decide which complex goes with which color. And then you can come back when you're ready to see my answer. All right, so you can analyze this from either direction. I'm going to go ahead and start with the observed color. And I like to make a little table like this just to sort of organize my thoughts. So observed color, and then change that to absorbed color, and then say if this is, in this case I have two complexes, so stronger or weaker field ligand relative to one another, and then I will identify the compound. All right, so my observed colors, I have violet and I have green. Whoops, green, which I'm having trouble writing. All right, so violet, opposite the color wheel, is yellow. Green, we already said above, opposite the color wheel, is red. And so now to answer this next column, I have to know which is higher energy, yellow or red. Red, again, is the lowest energy, visible light. So in fact, yellow is higher energy. So maybe I'll put an intermediate column here. Higher energy and lower energy. Therefore, yellow must be associated with the stronger field ligand, and the absorbed red light is associated with the weaker field ligand. So I have two ligands here, H2O and NH3, so now I just need to go see which one is which. And I go up to my spectrochemical series. We're not looking at chloride and water now, we're looking at water and ammonia. And in fact, in this case, ammonia is the stronger field ligand. So it's going to absorb the higher energy light, and in this case, water is going to absorb the lower energy light. So they're right next to each other, but ammonia is in fact a stronger field ligand. So this ligand is ammonia, and this ligand is water. All right, so that's my work. My final answer then is that, all right, so the first complex I was given with water, that is the weaker field ligand, so that one is green. And then the other one, which is nickel with 6 ammonias, and I didn't check here, but you can, that both of these are nickel 2 plus. Both the ligands here are neutral. You have to compare the same metal when you're comparing ligands this way. So nickel 2 plus then is, with the ammonia ligand, is the stronger field ligand, and so that one is violet.